Very what's up, guys? Yeah, so I want to make a small video, probably a few small video talking about algebraic integers. And yeah, because I find algebraic integers is important and some of the notation that we will keep using in our videos. So I want to introduce algebraic integers and algebraic numbers. And basically, I will talk about some interesting things. Okay, and I hope you guys subscribe to my channel if you want to see more strange mathematics or however things that you can check out my video. So in this video, I will talk about definitions. Okay, and okay, so let me just maybe use orange or yellow. Okay. Okay. So before we start, let's define a number field. So very simple number field. When number field just a finite field extension of it. So just speaking, it's a finite extension. Okay. So what finite extension over Q? I think everyone knows about this K. So basically, simply speaking, it's K the finite dimensional Q space, Q vector space. Okay, so if you don't know about what is field extension, then maybe you should check out Galois theory or something for just basic. And then usually we will denote this to be the degree. Okay, so this is degree of such. This is called degree. Basically, it's the degree of the dimension of the vector space. Okay, or simply speaking is that any element belongs to K. Okay, or I should say there's a basis, right? So like basically there's a, let's say K1, K2, Kn belongs to K, such that for every x belongs to K, one can write x equals to A1, K1, A2, K2, An, Kn, and all the Ai belongs to K. Okay, so simple example. The first example is the standard one, which is Q square root of 2. And the joint square root of 2, basically A plus B square root of 2, and AB belongs to Q. And obviously that the dimension of Q square root of 2 over Q is basically the 2. Okay. And because right, so you can see that the 1x and the 1x square root of 2 are bases. And notice that there is a theorem that basically the dimension of that L of the K over K alpha over K will be the degree of the minimum polynomial of alpha over K. So this means that in order to make this finite, that alpha must be algebraic over K. So alpha must be algebraic over K. So in this case, that the square root of 2, the minimum polynomial will be x squared minus 2. So the dimension is 2. And the second example is that if you define omega n to be exponential to pi divided by n, this is called n roots of unity. So this n roots of unity, if you add a joint with q omega n, this is called the cyclotomic field. So this one is famous one, cyclotomic field. And I think the degree everyone knows it, right? It's the famous Euler-Torsion function, or Euler phi function. So this is also a number field. Okay, so now let's define the algebraic integer. So when I say something is algebraic integer in the number field, the number field K means that let's say alpha. If alpha is an integer called algebraic integer in the number field K, means that this is alpha belongs to satisfy the two properties. One is alpha belongs to k. The second one is that there is a monic polynomial. There's a f belongs to c of x, and f is monic, such that the f alpha is true. Okay, so simply speaking, is the element in k and also satisfy the monic polynomial. Okay. So one obviously that the algebraic integer is obviously just the k intersection with all algebraic integer over q. It's basically the algebraic integer. For all algebraic integer, like in the order of algebraic number, such that the algebraic integer is a subset of algebraic number, and you take all these algebraic integer, basically it's all the usually the second condition. If your alpha only satisfies the second condition, that we usually call algebraic integer. So usually the algebraic integer in number field k just the algebraic integer intersection with the original k. Okay, so this usually when somebody say algebraic integer, he or she just related to the second condition. But when I say the algebraic integer in the number field k, then I assume that this alpha also need to sit inside k. Okay, and so now we have another definition, which is for algebraic number. So algebraic number is very simple. So when I say alpha belongs to k, when I say alpha is an algebraic number in k, need to satisfy the first one is alpha belongs to k. The second one is there is a rational polynomial. There is a rational polynomial f belongs to q of x, such that f alpha equals 0. But by the way, f cannot be 0, and also in this case f cannot be 0. And in this case, that actually one can also choose f to be monic because it's rational, right? So you can you can just divide every coefficient by the leading coefficient. So you can just assume that this f is monic. Okay, so now let's see. Maybe for example, right? So if you x squared minus 2 is a number field, right? Because you can take q the square root of 2, and obviously the square root of 2 divided by 2 square root of 2 is in the q square root of 2. This guy is algebraic integer. Okay, and also I in the q as a joint I is also algebraic integer. Okay, so usually notation, if we have the number field k, then we will use OK to be the algebraic integer of in k. So it's a set of algebraic integer Okay, and yeah, and there's a fact that I think this fact is maybe I think I don't want to prove this fact, but this fact is simple. I think just from algebra. So this theorem says that the minimum polynomial of alpha has integer coefficient if and only if alpha is algebraic integer. Okay, I think this the minimum polynomial of alpha basically is the f belongs to q of x, such that f of alpha is 0, and you need to choose f to be the smallest degree. Okay, and you can assume f to be monic. Okay, so in this case, that since f is monic, right? So you can, in general, this f just to be q of x, but okay, so if f, you can see this proof, right? This direction is simple because when alpha is algebraic integer, that you can probably not simple, right? But when alpha is algebraic integer, that you know there is a integer coefficient equation such that this is true, which is monic, and you can prove that this will imply that the minimum polynomial of such f must have the coefficient integer. So this proof is like using basically the similar proof as Gauss lemma in the abstract algebra. So yeah. So I want to prove it very simple. Okay. And using this, that you can easily prove the fact that the Q intersection with the algebra integer. So algebra integer, all the algebra integer will just be z. So simply speaking, that the only algebra integer which is rational must be the integer itself. Okay, the proof is very simple, right? You're just using x minus a divided by b. If you take element q is a divided by b, then you consider x minus a divided by b. This is the minimum polynomial of a divided by b. Then by this lemma, this a divided by b must be integer. If a divided by b is algebra integer, then prove that a divided by b must be integer. Okay, so now yeah. But the fact that I need to prove this is important. So there are two facts. The first fact is that algebra number forms a ring. So it's trivial, right? Because all the number field is a ring. So then the number field is already a field. Okay, must be a ring. So trivial. But second fact is a little bit non-trivial. Basically, says that all of K is a ring. So this means that if you take two algebra integer, the sum of them must be algebra integer. If you take two algebra integer, then multiplication must be algebra integer. Okay, this is a little bit tricky. It's maybe hard to prove, right? Because it's not necessary that you can find if you can find the monic polynomial for alpha and the non-monic polynomial for beta, then it's not necessary that the sum of the guy must be another monic polynomial. Or easy to find another monic polynomial such that its alpha plus beta is the root of such monic polynomial. Okay, so in order to do this, we need a lemma. We need a following lemma. We will say that say the following. Okay, so if alpha belongs to OK, if and only if the z of alpha is finitely generated. Okay, so simply speaking, that z of alpha finitely generated margin. Okay, so to be more precise, this is what I want to say. So z of alpha is finitely generated Z margin. Okay, so basically this means, as I say, right, this means that so finitely generated means that you can create a surjective map from B to N to Z to alpha. Okay, or simply speaking that as I said, right, so you can find basically any x belongs to or x belongs to alpha. You can find alpha 1, alpha 2, alpha n. So alpha 1, alpha 2, alpha n are fixed in Z of alpha. But you can find beta 1, beta 2, beta n in Z, such as x is a linear integer combination of beta 1, alpha 1, beta n, alpha n. You have a basis, our basis, and then you can find the integer combination of such basis, or will generate all the Z of alpha. Okay, so yeah, and yeah, I think maybe I use this more. Yes, we use this. Z at join this alpha, right, as a Q at this alpha. And this finally generated means that you can find alpha 1 to alpha n element in this, right, such that fixed and such that for every x that you can find all the beta 1, beta 1 to up to beta n belongs to Z, such that this x is the integer linear combination of such guy. Okay, so proof. So one direction is simple, right? So let's say alpha is algebra integer. Then we know that we have alpha n, right? You can return that some alpha n can be written as minus of n minus 1, alpha minus 2, minus alpha n minus 2, alpha minus 2, minus alpha 0, and all these alpha I are integer. Okay? This means that any guy which is higher than alpha to n can be replaced. So this means that our join alpha basically is the direct sum of the z with so z alpha is basically the direct sum of z alpha, the direct sum with z alpha squared, the result of z alpha cube, also maybe z of alpha n minus 1, right? Because any linear, any polynomial, yeah, this is the same as, yeah, so any polynomial, right? This addition alpha, basically you take the finite sum of this alpha power, and then you go to alpha n, you can replace it with right? So any of these guys must be generated by the first n minus 1, because up to alpha n, then you can replace to be all the integers. Okay, so this one is like simple, right? This basically. And obviously that any guy here is also in the right hand side, right? So it should be okay. Let's say another direction. So in another direction is that we want to show that if this guy is my generated Z module, basically this is true, then alpha must be algebraic. Okay, so the proof is very a little bit tricky, right? So okay, so we can assume that these guys finitely generated. Okay, so that means that you can take the final generation, right? So I can take each AI to be will be polynomial of alpha. So each AI will be, let's say f1. So I can take AI to be f1 alpha, and then maybe alpha an to be fn alpha. Okay, and all this has integer coefficient, right? So that means that if I can take, so there are f1, f2. So this there is a degree f1 and a degree fn. Okay, then I can take n to be greater than all the degree. Okay, and I take alpha to the n. Okay, so alpha to the n is finally generated, right? So must be summation of gi fi, right? I from 1 to n, and then gi is okay. But this means that if you consider equation as x for n minus gi fi of x, I from 1 to n, then this polynomial is monic, right? Because the degree capital N is larger than everything, and the alpha is a root. Okay, so this proof alpha is algebraic. Okay, so this is so once we have this, then we can prove back that okay. Proofs are very simple because if you take two algebraic integer, then this guy, right, is a subset of finally generated Z module. Finally generated Z module basically is free abelian group. If you in terms of Z, so this and also this. Okay, and okay, so if they are all subgroup of these, and these are algebraic finally generated, so these two are finally generated. So this proves that alpha plus beta and alpha beta are all algebraic integer. So the final theorem that I want to prove in this video is the following. So basically, I want to say that if you take Q times all the algebraic integer, K that will be as a set will be K. Okay, so any element in the number field must be rational point of algebraic integer. This is a little bit, you think a little bit, but it's a deep object. I think it's very interesting. Although the proof may be simple. Okay, so one direction is simple, right? One direction is the Q of K will be K. This is simple, right? Because the K is a field, right? So Q in K, because K is finite extension over Q. So this thing is trivial, right? Trivial because K is a field. Right, in the K, sorry, Q in K and also OK in K. Okay. Now the second directions may be difficult. So what we need to show is that you take any element A. Right? So you take A in K. We want to show that there is B in Q, such that B we want to take any K. We want to say that this K, right, can be written as B times some algebraic integer. Okay, then B is rational. Okay. So okay. But this Q, right? This Q can be can do the reverse. Right? This Q can do the reverse. Okay. So actually I can show is I can make a statement which is a little bit different. I can make a statement say the following. I can say that I want to say something. I want to say that if let's say I take alpha belongs to K, and we want to show that there is a D which is integer. Right? This is very interesting. It's integer such that alpha D belongs to OK. Okay, so this fact, right? This means that if alpha take K and then you take D, right? Prove that D alpha belongs to OK. Then basically you prove that any alpha can be written as 1 over D OK, and 1 over D belongs to Q, right? So it proves the results. So it's the same thing, okay? It's the same thing that if you take alpha belongs to K, right? And then you take that, you times some integer, which will be OK. This is the same as you can just take 1 over D to be rational and take this and 1 over D to be this rational. And yeah, and the D alpha belongs to OK. So 1 over D times D alpha will be anyway in the original in K. Okay, so this is what we want to show. Okay, so proof is basically follow the simple idea. So we just take the minimum polynomial f of alpha. Now I will take f to be 2 of x, and f alpha is 0, and the f is 0, and the f is monic, right? Because it's rational, so I can always choose to be monic. The f is monic, so I can write f to be like x to the n, and it's rational. I want to make it like using an minus 1, bn minus 1, minus 2, and an minus 2, bn minus 2, 2, a0, b0, and all the AIR belongs to Q. And what? I wanted to create a D. I want to say that I can write a D, which is D may be very large, but this is true. So I'm getting D to be the LCM of Bn minus 1, Bn minus 2 of the B0. Okay. And so I can define a polynomial called G to be, let's say this is f of x. So I take to be x divided by D and the D to the n. Okay, so let's do some computation. So this is f divided by D to the n, it's a n minus 1, Dn minus 1, x divided by Dn minus 1, a0, b0. Okay, so your easy calculation is that the leading coefficient is still x to the n, and then this one will be integer because this will be Dn minus an minus 1 divided by Bn minus 1, but D is the least common divisor, so this guy will be integer, and you can keep showing, right? The rest will be the integer. Okay, so G is the of x, and G is monic, and G of the alpha is the root, right? It's 0 because x divided by D, right? So alpha is the root, right? So alpha D is the root. So alpha is the root of f, so alpha D is the root of f. So the alpha will be the algebraic integer. Okay, yeah. So I think this is our all the videos. And next time that I will introduce the two famous object or two famous functions on the number field called the norm and trait. So hope you guys enjoy. See you guys in the next video.